Welcome back, geometry students. Mrs. Fallon here again. We are on page 293, section 10.4 for our geometry student journals. So what we're going to talk about in this unit is, again, some different properties and some theorems, a few different vocab terms that we're going to get into, and then I'm just going to kind of walk through some examples so you can kind of see some of those theorems kind of played out in some examples, so before you kind of go practice this on your own. All right, so we're actually going to start on page 293 at the very top. And there are some definitions in here that I kind of just want to make sure that we read through. So it says an inscribed angle is an angle whose vertex is on the circle, whose sides contain chords of the circle. So what I want to get at here is an inscribed angle, and maybe it's helpful if I kind of show you a diagram here. I'm gonna kind of scooch over to page 295, where it kind of gives us our definitions. An inscribed angle. So if I have a circle, right, an inscribed angle means that you have an angle, okay, that's all inside of your circle. So it's inscribed inside of the circle. The vertex is on the circle, so it's not hovering somewhere in the middle. And notice that these two side lengths of your angle are considered chords. So like this would be a chord of the circle, this would be a chord, because those are both line segments where the endpoints are on the circle. So this is what we call an inscribed angle, all right? That's what we call an inscribed angle. The next part says, an arc that lies between the two lines, rays or segments, is called an intercepted arc. All right, so the intercepted arc means the part of the circle. So if you look at an inscribed angle, it's the part of the circle, so the part of the circumference of the circle, that is between the two kind of ends of the angle. So we call this the intercepted arc. Just so we can label it here. So this is the intercepted arc, whereas this is our inscribed angle. So that's what that means. Intercepted arc, inscribed angle. Those are the two kind of most important, I guess, definitions in this section. The rest, it says a polygon that is inscribed polygon when all vertices lie on a circle. So what that means is if we have, let's say, if I have, let me make sure I have all this correct. If I have a polygon, so think like a rectangle, a pentagon, an octagon, whatever the case may be. If I have a polygon inscribed, which means inside of a circle, an inscribed polygon, I'm just going to draw kind of a small little example here, would be, let's just draw kind of any polygon here. All of the vertices of this polygon have to fall on the circle. So notice I drew a pentagon here. This is called an inscribed pentagon or inscribed polygon, right? And so all the vertices lie on the circle. That's what it means to be an inscribed polygon. The circumscribed circle is the circle that does inscribe the polygon. So these two definitions are kind of referring to the same picture. The inscribed polygon is referring to the polygon, so that's the pentagon that we're talking about in the middle here. The circumscribed circle, which is kind of a weird word, but that's referring to the circle that goes around it. So that's what both of those mean, I guess, is what we're kind of getting at. The only other definition here that I want to talk about is something called, so we have an inscribed angle, we have an intercepted arc, we have inscribed polygon and a circumscribed circle. The other thing is something called subtend. Subtend is if the endpoints of a chord or arc lie on the sides of an inscribed angle, then the chord or arc subtends the angle. Okay, so this is kind of what it means. So I'm going to go back to this little picture up here. So the definition says if the endpoints of a chord lie on, or an arc, lie on the sides of an inscribed angle. So notice how this chord right here lies on the sides of that inscribed angle. Then so this word means that this chord subtends the angle. And that's just a definition. To be honest with you, I've never really, I don't think I've ever used that terminology, but it shows up here, so I thought I would kind of at least mention it. Here's another, like a picture down here. So this chord right here subtends this angle. And again, it's It's not a huge thing. I think there's a vocab, one of the theorems kind of mentions that in passing, so that's where it's going to come into play. So we'll talk a little bit more about that here in a bit. All right, let's look down at the bottom, page 295, 1010, measure of an inscribed angle theorem. So this is actually a pretty basic definition, but a very important one. So let's say I have a circle, and let's say I have an inscribed angle. So here's my inscribed angle. We'll call it X for fun. And I'm going to measure this intercepted arc of 40 degrees. There's a relationship between an intercepted arc and its inscribed angle. This inscribed angle is half the measure of its intercepted arc. And that's what this is saying here. So this angle here, this inscribed angle, is half of this arc. So this means X is going to equal 20 degrees. So inscribed angle is half of its intercepted arc. So that's a rather important, I guess, definition or theorem that you're going to want to make sure you know. Inscribed angle is half the intercepted arc. All right, let's do some more. So 1011 says inscribed angle of a circle theorem. If two inscribed angles of a circle intercept the same arc, then the angles are congruent. So this kind of makes sense. So look, if I have this inscribed angle, right? Arc AB is its intercepted arc. But then if I have this angle right here, well, let me use a different color. Then if I have this inscribed angle, its intercepted arc is also AB. So since both of these inscribed angles have the same intercepted arc, let's just say this arc was 100 degrees, then that would mean that each of those angles have to be 50 degrees. So the measure of angle D and the measure of angle C in my little example here would have to equal 50 degrees. And the reason why is because they both make up the same, like the inscribed or the intercepted arc is the same for both. All right, a polygon is inscribed polygon when all its vertices lie on a circle. The circle that contains the vertices is called a circumscribed circle. And so we talked a little bit about that in the previous page, and this is just kind of a nicer diagram for it. Next theorem says inscribed right angle theorem. If a right triangle is inscribed in a circle, then the hypotenuse is the diameter of the circle. Conversely, if one side of an inscribed triangle is the diameter of a circle, then the triangle is a right triangle, and the angle opposite the diameter has to be a right angle. In other words, if we know there has to be a right angle inside my circle, okay, the only way that's going to exist is if the hypotenuse, which happens to be the longest side of the triangle, also is the diameter, because there's no other longest length inside of a circle, right? So that's all they're getting at here is if you know there is a right triangle inside this circle, inscribed inside of a circle, then the hypotenuse has to be the diameter. That's really all they're saying here. All right, last one on this page, inscribed quadrilateral theorem. A quadrilateral can be inscribed in a circle if and only if its opposite angles are supplementary. This is kind of referring back to our polygon unit, where basically we're just saying that whether it's inscribed inside of a circle or not, what we know is these opposite angles are supplementary. And I used the wrong definition or the wrong drawing here, but basically what we know is these two angles. So D and F have to add up to 180, E and G have to add up to 180. So opposite angles are supplementary. All right, let's do a few examples just so we can kind of put those theorems into practice. So we're going to do page 297, and we're just going to kind of go through all of the stuff on this page. So let's start. Use the diagram to find the indicated measure of angle A. So again, notice what we're given here. We're given that this is 28 degrees. We're given the side length is 3.9, the side length is 7.3. So one of the things I know is, again, if we know that this is a triangle that's inscribed inside of our circle, okay? So one of the things I want you to recognize, since this side right here is a diameter, then this has to be a right angle, okay? So since this side is a diameter, this has to be a right angle. So the measure of angle A has to be 90 degrees. All right, so if that's 90 degrees and this is 28, then we can kind of subtract from 180 or subtract from 90 to get angle C. So the measure of angle C I got to be 62 degrees, because 62 and 28 and 90 add up to 180. All right, the length of BC. So what we're getting at here is the measurement of BC. We are given 3.9 and we're given 7.3. Since this is a right triangle, we can set up the Pythagorean theorem. Now remember, Pythagorean theorem only works with right triangles. So that's the only reason why we can do this. So a squared plus b squared equals c squared. 3.9 squared, I got 15.21. 7.3 squared, I got 53.29. Add those together. And then let's square root both sides. And you would get plus or minus here, but again, because we're talking about the length of a side of a triangle, we're going to only use the positive answer. So the length of BC is 8.28. All right, let's do the arc AC. So one of the ways to measure the measure the arc AC is to look at its inscribed angle. So that would be the angle that makes up this arc. So if this angle right here is 28, so remember the relationship between an inscribed angle and its intercepted arc. This angle has to be half this arc. So if this is 28 degrees, then the arc has to be twice as big, which in this case would be 56 degrees. Next is A to B. So arc AB is right here. One of the ways you can do that is, again, if you look at the inscribed angle. So if I look at this inscribed angle, so ACB, see how the ends of my angle make up this arc. We already know that this is 62 degrees. Remember, we figured that out in this step here. So we figured out this angle, angle C was 62 degrees. That means this arc has to be twice as big. So if that's 62 degrees, the arc has to be twice as big, which means it's 124 degrees. All right, let's look at this one. Name two pairs of congruent angles. All right, so one of the things I know is that in this triangle, okay, so we have, I know, well, I mean, technically you know these two angles are congruent, right? Because they're vertical angles. And if these two, okay, so the other thing that's kind of weird here is you have to kind of look at the inscribed angles. So notice that this is an inscribed angle, and let me see if I get a different color here. This is an inscribed angle. Do you notice that they both have the same intercepted arc of BC? So remember that theorem we talked about on the previous page. If two angles have the same intercepted arc, then those two angles have to be equal. And so we could say angle A is congruent to angle D for that reason. Now we could say those 1 and 2 were congruent because of vertical angles, but let's use one of the theorems that we did on the previous page. I'm guessing that B and C, so if angle B right here has this arc, AD, as its intercepted arc, that look at angle C, it has the same intercepted arc, which means that angle B has to be congruent to angle C. So again, they both have the same intercepted arc, which means those angles have to be equal to each other. All right, last but not least, on number 7, we're using that property that we know that opposite angles of an inscribed polygon have to be supplementary. So again, what we're kind of getting at here is we're saying n plus 100 has to equal 180 degrees, which of course n has to be 80 degrees. And then same, m plus 65 has to equal 180 degrees. So m has to equal 115 degrees. So again, that's just using that other theorem, talking about an inscribed polygon and that the opposite angles are supplementary. All right, nice and short video today, just kind of using those theorems. What I would suggest that you do is, again, go back through big ideas, make sure you're able to do the problems, come to class with any questions. All right, that's it for now. Bye.